Hello everyone, welcome to a new video. In this one, we're going to talk about a specific algorithm for clustering. The name is Dbscan, Density-Based Spatial Clustering of Applications with Noise. It's a very intuitive algorithm, I really like it. So let's see how it works. So first, let's try to highlight some differences with the popular k-means algorithm. So in k-means, the key idea is to cluster the points based on the distance that they have. So for example, if we have this initial shape, this figure here, so you can see that ideally we'll have like two groups, this one and this other group. But k-means only focuses on distances, not in patterns. Therefore, it will find like a centroid here. It will be the first cluster for k-means and another one in this area. So it will group together these points, even if they don't belong to the same pattern. The second one will pick something like this. We have a second figure, like this one, where we have two circular figures. So k-means will do the same. It's gonna pick this and this. Now in the case of Dbscan, it will analyze the density. It will put together points in the same cluster if they are located in high density areas, and if you can find paths to connect those points. Because it's interesting, because in Dbscan, if you notice, it's finding two clusters, this one and this one. Is capturing a non-convex region, is a non-linear area. And it's interesting because there are some points between the two clusters. For example, these points here and here, they are closer compared to points here and here. However, if you see there is a space here, it's like a low density area. So that's why Dbscan is not grouping those points together, right? But if you focus on the, like the outer parts of the first shape, you see that there is a path of high density that will connect these two. So Dbscan is capable to identify non-linearities, and that's why it is really interesting. And it's not just a density base. That doesn't mean that Dbscan is always better than k-means. I just want to highlight some of the differences here. So some nice things about the Dbscan: there is no need to define k, or the number of clusters. You don't know that. The algorithm will find. Another nice thing of Dbscan is that if there is a point that it's in a low density region, let's say that you have a point here, for example, this region is far from the other points, then this point won't be included in the clusters. It's not like k-means and other techniques that every single point in your data is going to be assigned to a group or to a cluster. That's not the case of Dbscan. If there is a point in a low density area, then that's considered an outlier, which is nice because in addition to finding clusters, you can also use this technique to find outliers or typical data. Okay, so let's try to understand how it works. It has two parameters. These are more like hyperparameters, to be honest, because you need to define them before like running the algorithm. So the two parameters are the epsilon and the minimum number of points. So the epsilon is just a distance, the EPS is just a distance. So, and the number of points is like how many points should be in that distance or in that region to consider that point as part of the cluster. So let's see how it works. So here we have a point here. If you see, the epsilon or EPS is like a radius. So we can create like a circle, right, around our point. Now the criteria here, you need the two, the distance and the number of points. So here the mean points is 5. We will see how to find these numbers later. So if you have 5 points in this region, including the point that you're evaluating, that's also part of the criteria of the mean points criteria, then that's considered a core point. So here we have 1, 2, 3, 4, 5, right? That's why this point here in the middle, it's a core point. It means that it's part of the cluster, and also it's an important point. So you can repeat the same idea with the remaining points. So for example, if you do the same for, let's say, this one here. So using the epsilon, right, we create a circle, which you can see here in the figure. So if you notice, there are only 1, 2, 3 points. So we're not satisfying the minimum number of points, right? So this is not a core point. But why is going to be included in the cluster? Because in the EPS or in the region, we have a core point, this one. So if a core point is included here, then even though this is a border point, it's part of the cluster. This one is part of the cluster. So far we have core points. They will satisfy the two requirements, right? Like the number of points, minimum number of points within the region. But in the case of the border, that condition is not satisfied because we don't have the minimum number of points. However, since there is at least one core point, then we consider this as part of the cluster. Now let's see the third category of points that we will have, this one. If you create here with the EPS and you evaluate how many points you have here, so there are only 2 points, including the point that you're evaluating, right? Just 2 points. So it's less than 5. And in addition here, we don't have core points. Then this is considered noise. It's like an outlier, an anomaly, right? Because it's in a low density region. So that's how it works. So we will classify 3 points. Let's summarize that. We have the core points. They have at least the minimum number of points, which is a parameter in our model within the EPS. Remember, this is like a distance, the radius, to create the circle where we count the points. Then we have the border points. So they have fewer than the minimum number of points within the EPS, but as we see in our previous example, in the EPS distance, there is at least one core point. So core points and border points, they are assigned to a cluster. Now, in some cases, there are observations that when we create the region with the EPS and the minimum number of points is not satisfied, then and there are no core points in that region, then these are outliers, it's just noise. So they are not assigned to a cluster. So how can we estimate the minimum number of samples or minimum number of points, mean points? So there are different rules, but these are not like strict rules. These are guidelines to give you, like a way to compute this. So one idea is, okay, the minimum number of points is just the number of dimensions plus 1. It's a simple one. So if you have 3 dimensions, you can use 4 points, like to find within the EPS region. Another possible rule is just 2 times the number of dimensions. So let's say that you're working in 2 dimensions, 2 variables, then you will need 4, like 2 times 2, right? 4 minimum number of points. So typically this value will be between 4 and 10. So you can evaluate, right? You can change the value, you can see the sensitivity and see how it changes to make a decision. Okay, so this one, then we have the second parameter, the EPS, or the distance. So in order to do this one, we need a k-distance graph. It's a simple graph. So the idea is like using the minimum number of points. Let's say that we define that our minimum number of points is going to be, let's say, 4. Then we create a 4-distance graph. K-distance graph, we use a 4-distance graph. So we use the minimum number of points as k, or a value that is close to that one. The idea is that for each point or for each observation in your data set, you find the distance to the k closest observation. In this case, if k is equal to 4, so you will find the distance to the 4 closest observations, and you compute the average distance, right? And then you organize from the smallest to the largest distance. So you will get something like this. So here in the x-axis, you have the observation, the number of observations, and this is organized. So this plot will always look like this. It's going to be increasing, right? In the y-axis, we have here the distance. So here is where we're going to get our EPS from this distance. And we use the knee or the elbow method. So we see, or we try to see at which point this plot is going to increase significantly. You see like the change in the slope that is dramatic. So here, for example, you see that it's increasing, but here it increases dramatically. So that will be your knee, right, or elbow. So with this, you can get your distance. So in this case, it will be something between 0.1 and 0.2, 0.15. And again, this is just a guideline. So you will need to test those values and see like how good are the clusters that you get, if they make sense. Okay. So let's go over a couple of examples before we conclude. So these two examples are available in our Brightspace and also below this video. I will make them available. Okay, so the first one is the same example that we checked in the slides. So this is our data. Let's see. This is our original data, right? We have like two clusters. We know that this is a simple example because this is in 2 dimensions. However, in real life, if you are multiple variables, it's going to be a little bit more challenging to visualize. So most likely you will need some like dimensionality reduction techniques to be able to visualize that in a lower dimension. All right. So we find EPS and the minimum number of points. So for minimum number of points, since there are 2 dimensions, you can use 4, right? You can test 3, 4, 5 if you want. For the EPS, we need to compute the plot k distance graph. So remember, if I'm going to use k equal to 4, minimum samples equal to 4, then we compute the distances from each observation to the 4 closest observations to that one. And then we organize them from the smallest average distance to the largest distance. So that's what we're getting here, right? That's what we're getting here. And now you can see like in which region is changing, right? So you see here, somewhere between 0.15 and 0.20, right? The distance between 0.15 and 0.20, you see that increases dramatically, right? So your EPS will be in this region, right? You can pick somewhere 0.18, 0.20, okay? So let's see how it works. So now let's apply Dbscan with the 2 parameters, EPS value equal to 0.2 and the minimum number of points equal to 4, right? So the Dbscan, you can find it in scikit-learn, right? So we just apply the EPS with our value 0.2, minimum number of points with our value, which is equal to 4. And then we just predict or find the groups for each of the clusters for each observation. We can visualize that. So we get 2 clusters, 150 and 150 each. This is it's synthetic data, so that's why it looks that perfect. So it's capturing right with 0.2 and 4. It's getting the patterns right. Now you can perform some parameter sensitivity analysis if you want, like change the EPS, or if you want to change the minimum number of points. So that's possible just to see how it works and to get a better understanding of the differences. You can also compare it with k-means, as we did initially in our lecture. So you see here, for example, you have k-means. So please notice that it's mixing the points, right, from different regions. Even it doesn't matter if there are low density areas between the points, right, like here. So that for this specific example, Dbscan, of course, it's a better alternative, right? There is another example here, which is very popular. You will see it in a lot of videos, and it's using a smiley face, right? So we can, if we have these are our observations. So to the left, we have k-means, to the right, Dbscan. So originally we have, the happy face. So the perimeter of the face, that's like a one cluster. Each eye is a different cluster, and then the mouth, right? So with Dbscan, it will group together the perimeter of the face. If you see, it's like yellow, right? That's cluster 1. For each eye, it's going to be a different cluster 2, and the mouth, right? But if you use k-means, it's going to mix, like some part of the face with the eye, some part of the mouth with the face. So because it doesn't capture patterns, It's just based on distance. If you notice in the plot to the right, there are some points with an X. It doesn't have like the other colors. That means that those are noise or outliers because they are in low density areas. They don't meet the criteria, the minimum number of points within the EPS region, and there are no core points within that region for them. So that's why they are not part of a cluster. So that's a nice thing about Dbscan. It's not gonna force to assign each point to the to to a cluster. All right. So I'm gonna finish the video now. I'll see you in our next lecture.